Greetings. In this video, I'll be working on a couple of examples on doing a chi-square goodness of fit test and showing you how the hypothesis testing procedure works when you go through a problem. Let's look at this one. In a study of fatal car accidents, 245 cases were randomly selected from the population in which a driver had a blood alcohol level above the legal limits. The results are listed in the following table. So, as we all know, the given information in the problem here is labeled as O's, the observed frequencies. So the number of O's here is O1 is 29, O2 is 30, O3 is 33, and so on. It's asking us to use a 0.01 alpha to test the claim that the frequency of such fatal accidents is uniformly distributed throughout the week. Okay, so uniformly distributed throughout the week, right there I know, and since there's no other percentages given in the exercise, I know we're talking about a goodness of fit where all the probabilities are uniform, meaning the same. So what the claim is here is that the probability of Monday, I'll cut it as P1, is equal to P2, is equal to P3, is equal to P4, P5, P6, and P7. And if they're all the same, that means each one has to be equal to 1/7. So that's my claim, and hence that's my null hypothesis. So my null hypothesis is that all the probabilities are uniformly distributed. So you could write, instead of writing something mathematical, you could write for your null hypothesis, probabilities are uniformly distributed. I mean, I've seen a null hypothesis and a goodness of test, which is just a statement, has nothing to do with mathematical symbols. But it's a math class, so we're going to have to use the mathematical version of that statement. So instead of writing the probabilities are uniformly distributed, we're just going to actually write the mathematical statement for that, which is P1 equals P2 equals P3 equals P4, P5, P6, P7, and all that equals 1/7. And that's how you write your null hypothesis. And ergo, a multinomial experiment, because more than two P's here. If you had 1P or 2P, then it would be one or two hypothesis testing for one population, two population, but this is multinomial experiments, and that's exactly why we can't use a normal distribution. We have to use a chi-square distribution, ergo the name chi-square goodness of fit. Anyhow, my alternative is the statement that says at least one is different, and that's uniform, right? Meaning it throughout all the problems is just the same. And I can abbreviate it to alloyed. At least one is different, and that is my step one. Now my step two is calculating the test statistics. Now, as you've seen, the test statistics in the goodness of fit test is a chi-square formula. It's the summation of observed frequencies minus expected frequencies, quantity squared, divided by expected frequencies. So every time you see a process like that, you immediately realize that requires a table. Now, you could do it with pencil and paper, which is what people used to do 50 years ago, you obviously have to list all your O's, which is like 29, 30, 33, and then you have to list all the E's, and we'll see how to calculate those. And then once you have all the O's and the E's, then you calculate this O minus E quantity squared divided by E, and then you write those down here, and then you ultimately add them all up, and that would be your test statistics. And it used to be done with pencil and paper. But thank God for creation of what's called Excel and spreadsheets. We don't need to do that with pencil and paper anymore and go through a lot of pain. I could just do that on Excel and get the test statistics. So let me move my screen to a spreadsheet so I could show you guys how we could enter this onto an Excel and get a test statistics out of it, which is the second step. So let me go to Excel. There it is. So I have it set up for you here. All right, so my test statistics here I'm going to calculate for you. This is the first problem out of the worksheet, so I've written here for you so you recall that P1 is 1/7, P2 is 1/7, P3 is 1/7, P4, P5, P6, and P7. So I've written that there so for you remember. Now I've written my O's here, 29, 30, 33, 34, 38, 43, and 38. Now my expected frequencies are, as you saw in the video, the way you calculate the expected frequency is to take the probability, the first probability, because that's the first expected frequency, and multiply that probability to the total of observed frequencies. So if I were to draw on this spreadsheet, I could just show you that E1, see, this is E1. This is the first E. This is the second E. This is the third E. And this is the fourth E, and so on. Now, how do you calculate your first E? You take the first P from the null hypotheses. And remember, this is the null hypotheses. So you take the first P from the null hypotheses, and you multiply it by the sum of your observed frequencies, 245. So it's almost like probability multiplied by sample size. Sort of, if you think about it like that. But that's how you calculate the expected frequency. Now, how do you calculate the second expected frequency? Well, you take the second probability, which happens to be the same, and you multiply it again with the same thing. That never changes. You always multiply it by the total. So you multiply that by 245. Well, let's look at the 30. How you figure that out? We'll go to take the third P, which again is one same, and multiply it by the same thing, 245. So you notice it's nice if all the P's are the same. If you're doing a goodness of fit problem where all the P's are the same, then all your E's will be the same, because you're multiplying the same probability to the same sum. So you just do it once and just drag it down, it'll be the same value. So let's try that so you could see it done here. So let's do that. So basically what I'm doing is I'm multiplying 1/7 to 245. So it's basically 245 divided by 7 is what I'm doing. And this one will be the same, so why bother? So I'm just gonna fill it, and there'll all be 35. Oops, I guess it didn't fill it. What did I do wrong? Oh, it needs dollar signs around A11, otherwise it's going to assume 0 because it won't see what's below 245. So you kind of, if you want to drag it down, you either have to put dollar signs around the letter, or you could just write 245 if you don't want it to ever change. And if you do that, and now you fill it, oh, good. So you could see a mistake that any of us could make. Good thing it came out. And I would have known anyways, because remember, you need to add the E's after you're done calculating them, and the sum of the E's and the sum of the O's have to be the same. If they're not, then you've made a mistake in calculating one of your expected frequencies. So it's a nice way to check once you calculate your expected frequencies as to whether you've done them correctly or not. Okay, so now it's time for us to calculate the test statistics. The test statistics would simply be O minus E, quantity squared, divide by E. So, and then I fill that, or I copy that down, fill it. And if I add them together, that'll be my test statistics, 4.23. Now the number of decimal places doesn't matter. You'll be instructed for that. So your test statistics is that number there. That's your test statistics, 4.23. So let's go back to our written work. All right, so my test statistics, which is a chi-square value, is 4.23, and I'm just going to use 2 decimal places. So here's my step 2. And this was my step 1. You've been used to putting it in the box. Now my step 3 is kind of nice, because in this chapter, as you've seen, the rejection region is not based on a uniform or T or a normal distribution. It's actually based on it follows the random variable here, follows a chi-square distribution. So your rejection region here is going to be step 3, where you graph, which you've been doing for the past few weeks. It's going to be a chi-square rejection region, meaning it's going to be skewed. And this is going to be the chi-square axis, and this is going to be 0 if you recall. Chi-square doesn't have any negative values. But the good news is that A, it's always going to be the same picture, and B, your rejection region here is always going to be a right tail rejection region. So you never have to worry about whether it's left tail, two tail, or right tail. So that's a good thing. So the rejection region here, for all the goodness of fit tests, and as you'll see, as well as all the tests of independence, for this entire multinomial chapter, the rejection region will always be a right tail rejection region. So that's going to be pretty nice for us not to have to worry about keep trying to decide which one it is. So there's just one less thing off our plate. Okay, so that's the rejection region here. And it's again always going to be a right tail rejection region. But there's some more good news coming. That's not the only good news. So first good news was that it's not going to be for you to worry about whether it's a z distribution or a t distribution. Here is only chi-square. Another good news was that it's always right tail, so that one is off your plate, so you don't have to worry about if it's left tail, right tail, or two tail. And the third good news is that the alpha value that you use here for your computations and for Excel and everything will always be just a given alpha, and you don't do nothing to it. You don't need to divide it by 2, double it, nothing. So you just, whatever it is, just run with it. So here, it says alpha is 0.01, which means the area in here is 0.01, which means that's the value I'm going to use for my chi-square critical value on Excel. So I need to find this gatekeeper again, if you recall. But here, this is not a z or a t. This is a chi-square value. So therefore, I need to use the chi-square dot inverse dot right tail command. So I'm just going to write it for you. Here is CHISQ chi-square dot inverse dot right tail. Here you put the probability, the alpha value, which is in this case 0.01. And your degrees of freedom is k minus 1 here, categories minus 1, since there are 7 categories of data here. Degrees of freedom will be that minus 1, so your degrees of freedom will be 6. So that will be the chi-square value that you can find using Excel. Now let me actually do it for you. 0.01 with 6 degrees of freedom. I can just type CHI chi-square inverse right tail. Probability is 0.01 and degrees of freedom was 6. So your critical value is 16.812. And that means that's where your rejection region starts from. Okay, so let's go back to our notability. Alright, so your rejection region starts from 16.812, so 16.812. So that's going to be the critical value that starts your rejection region. And now, just like before, the last step is decision. You look at the test statistics. Your test statistics here falls outside of the rejection region. So of course, if this is 0 and this is 16, then obviously 4 is somewhere there. So it falls outside of the rejection region, sometimes called the acceptance region. And we know when that happens, we have to say fail to reject the null hypothesis. Sorry. All right, so fail to reject the null hypothesis, which means the null hypothesis is actually true because you couldn't reject it. So the conclusion here is to say probabilities are distributed as expected. And those are two conclusions. You either say probabilities are distributed as expected or probabilities are not distributed as expected. If you rejected the null hypothesis, you would have said, well, then it looks like they're not the same. So you would say they're distributed not as you thought they were. So again, here you could clearly see that the null hypothesis is the status quo, and you try to reject it or fail to reject it or whatever. Here you couldn't reject it, so you say they probably are true and the distribution is uniform. Thank you.